at a global scale, and whether it's a planetary boundary. And so I want to start with a little history tale, and this is an age test if there ever was one. How many of you have read this book or remember the study? Yeah. See, this is the deal. The whole new generation has never even heard of it. Well, this was the very first Earth system model. And the title tells you everything. You saw it was translated 37 languages, 12 million copies, top-selling environmental title in history in 1972. You see what I paid for this baby? This is to me, my most valued book I own, is my original copy of The Limits to Growth. And what's interesting now is when you go, if you ever were to go back and read The Limits to Growth, and of course, what they were doing is doing a modeling of the Earth system in a very unbelievably simplified way by today's standards, to just see where humanity might be going in the future. And this was one of their graphs. This is about as good as graphics was back then. I'm sorry. This was what they called the standard run, and they were modeling in a general way resources, pollution, food, population, industrial output. What's interesting is they saw the entire Earth system peaking somewhere right about now. And by their analysis, from here on out, maybe here, it was going to be a serious downhill slide for humanity from somewhere around now into the future. And this was done in 1972. Well, the economists just lashed this model at the time. And it was widely not even critiqued. It was just laughed out. It was just laughed at in the economics world. In the global change science world, we paid a lot more attention because, this was the very beginning of our thinking at a global scale. It's hard for us to remember the pre-satellite era, but this is a pre-satellite era, and we hadn't started thinking globally yet. So this came out a week ago. Limits Revisited, a review of the limits to growth. We have the Pope on our side now. The time has come to accept decreased growth in some parts of the world. I thought that was, if you haven't ever read a papal encyclical, you ought to go read that one from last June. You'll see technical language you'll never, ever see again from a pope, I guarantee you. But one of the things they say here is if the Club of Rome's projections are right, then the next few decades are decisive. And that comes from this, from a week ago. And so that is, in effect, a preamble to my talk here, is why I'm bothering thinking about terrestrial NPP as a planetary boundary. Now, first, how many of you have seen the planetary boundary, are familiar with that term? Not that many. Now, isn't that interesting? In my crowd, I thought everybody heard of it. Okay, this was first published in Nature in 2009, and in effect, it's just a newer repackaging of the limits to growth logic. And Johan Rockström from Stockholm Resilience Institute, I had lunch with him a couple of years ago, and I said, Johan, did you have any idea that this would just explode the way it did? He says, we were clueless. We had no idea. The political world and the policy world has paid attention to this in a way that about the only other thing they pay attention to is our IPCC report. Otherwise, every single thing we write in science and nature and PNAS, they don't care about any of that. but somehow they've glommed onto planetary boundaries as this conceptualization of potential limits to growth of the Earth system. So to me, in a very literal way, a repackaging of the original 1972 thinking with some more explicit variables: ocean acidification, stratospheric ozone. This is much more technically rigorous than in the 70s. But in overall, it's the same sort of thinking that we better start paying attention to the capacity of the planet. And so this is my data set that my labs worked on for decades, net primary production of the world, computed every day at 1 kilometer resolution and then added up for the year. And so I started thinking, I wonder if this would be appropriately thought of as a planetary boundary or as a limit to growth. Well, it all starts with a Keeling curve, as far as I'm concerned. And Dave and I riding up the chairlift years ago, they're outside of Montana, Missoula. I don't need to talk this crowd through this curve, that's for sure. But it does philosophically, it's important for us to remember that until this curve, humanity could fool itself into thinking that we were tiny little ants on a giant planet and that there was no way we could really influence the whole Earth system. And it was the Keeling curve that was the first evidence that humanity was having a global impact. And so to me, this is where Earth system thinking started. And Dave said that they only really, about the early 70s, it took about a first decade of his data set through the 60s and really seen the trend start to develop. It was about the early 70s, 1972, where it started this first nascent thinking of Earth system science came from. I find it really amazing. This is what Keeling wrote in 1968. The rise in CO2 is proceeding so slowly that we may live our whole lives without perceiving the threat. Man, don't you wish that turned out to be true? I mean, I've read that, and this guy knew more about the global carbon system than anybody on the planet at the time. And he still thought we had a long time before we had to get concerned. All right, so that's my preamble. Now I'll start back at square one and with a tiny bit of history. That this is my background. I'm actually, you might say, a tree physiologist by original training. This is the only known picture of me doing my master's thesis because I did a lot of computer modeling and only a little bit of field work. No, I actually did way more field work back then. But I think back, and I talk to graduate students about this now. When we were in graduate school, it never, ever imagined that we would have to talk to journalists about our research, that we would have to justify our research in front of congressional committees, that we would be giving public talks to taxpayers about why all this matters and why they should care. It was the farthest thing from our mind. We thought if we just did good science and wrote it up in our journals, we were good to go. And I think now of the students today, they've got to be good at all that stuff on top of their science because the world needs them very badly, and they can't just sit in the corner and write papers for ecological applications. It's not enough. They have to do that and then go do all this. So I've spent my career in what you might say is scaling logic of terrestrial biogeochemistry, from that measuring transpiration of those little seedlings where I started, up through flux towers, and then finally up writing algorithms for satellites. I find it worth remembering where we started. I love this picture. I You see 1983, Inez Fung, some of you know Inez. This is what we knew about global net primary production when I started. And, and you realize we didn't yet have any global data sets, any global satellite record. And so to think how much of this was just make-believe even, so I find that hysterical to look at. Well, so right about the time Inez was writing that paper, I conceptualized for this funny little NASA document that quickly sunk out of sight called Global Habitability Science Issues. I conceptualized, well, here's how we could do NPP better. And it was using the satellite to measure the ecosystem in a simple way with leaf area index, the daily surface meteorology, and then I could run a little photosynthesis model on the fly, just pixel by pixel. And I thought, this ought to work. And so I thought this all through, and I could end up with net primary production from a simple carbon balance model executed for each pixel. And I figured it'd be way ahead of that slide I just showed before, way ahead. And I went back to my early training in plant physiology, and I thought, okay, what are really the most fundamental things that control what a plant does, any plant? And I don't worry very much about species, and most of my ecology friends hate me for this, that I can gloss over all their species with a blink of an eye, and they find that quite outrageous, but too bad to go global. And so I said, okay, we know when it goes below freezing, most all ecosystem processes go pretty close to dormant. So I could treat a threshold of freezing temperatures in a very direct way. Likewise, if we're talking about photosynthesis, when it's dark out, everything's all at zero. Again, so okay, we can calculate day length for anywhere on the planet and seasonally through the year. That's an easy one. Water gets harder to deal with, but we certainly know when there's no water, there's no plants. And so I came up with some really simple, almost trivial representations of climate influence on plant life in a very generic way, and built these algorithms defining those constraints for anywhere on Earth, because every single place on Earth is this combination of those three constraints: radiation coming into the system, the temperature, and the water availability. So it was really just representing those in kind of a different way, but not really theoretically anything brilliant. And just a simplified way of looking at it. And so we came up that globally, about 40% of the land surface is most fundamentally water limited, about 33% is most fundamentally temperature limited, and 27% radiation. And then we did this mixing to put it all together. One of the things we paid attention to, and this is kind of an aside, but I have always found this to be so much fun, I like to talk about it, is we would, in looking at extremes, we fell into this deal about looking at where the hottest place on Earth was. And this is a lesson for students that this isn't hot theoretical science one bit, but we got more public press from this than anything else we did, because they were always just enthralled by where the hottest place on Earth was. The people in Alice Springs, Australia, emailed us when we first published this, and because they want to brag about it for their tourism, would you believe? And what's interesting is it got boring pretty fast, because the first few years, this is a flaming desert in China and Australia, but then this Lut Desert in Iran wins over and over and over again. And you want to know why? Because that's what it looks like. We think Arizona's a desert. Arizona's like a tropical rainforest compared to this. Look at this. So, and this is because a scientist in Iran saw one of our papers in BAMS and sent me an email. Would you like to see pictures of this desert you're talking about? And sent us all these cool pictures. And yeah, talk about a low albedo surface that is bone dry. It's important that we can then recognize this is one of these places we won't be growing plants, and so our algorithm obviously eliminates places like that. And so what the algorithm did do is represent the plant cover by something called FPAR, which is the fraction of absorbed par. It's actually a radiometric measure of the leaf area of the canopy. It's really leaf area in radiometric units is what it amounts to. And so that was the measure of absorbed energy. And then there is simply a conversion efficiency factor, that how much of that energy gets converted to biomass. And a guy named Monteith came up with this back in the 60s as a shortcut for crop modeling. And it turns out to translate fabulously for remote sensing driven NPP. It's used all over the world now. And so all those, the daily meteorology just does is influence this conversion efficiency factor. And so you calculate gross primary production every day. You sum those up for the year, subtract some respiration costs, and you have net primary production for the year. And so this was my calculation of NPP that I could do anywhere on Earth. We compute 110 million cells per day. And so each one of those cells is just computed with this little algorithm, but then gives us our measure of GPP and then NPP. Now, we've been doing this now since the year 2000, and so now we can start looking at time series, and we can also look at variability from year to year and geographically. So just for example, in the summer of 2000, the big drought and heat wave clearly shows up, and the very following year when it starts raining, it clearly, the NPP goes up. So we, for years and years, have been looking at how well this algorithm represents what we really see on the ground of plant growth. Now, one of the things that I could probably say saved my career, I think you younger scientists will be amazed at this, but I wrote the original NASA proposal for this MODIS NPP with absolutely no validation plan of any kind. I've gone back and looked at the text. I couldn't think of any possible way to validate this calculation globally. Well, along comes the flux tower network, which, of course, up at Niwot Ridge, you have one of them here that's gone for years. And it saved me because it provided a highly calibrated tower measuring carbon fluxes. There's something like 400 of them around the world nowadays. And this is a good look at some of them. And yeah, they're just all over the place now. This became my validation plan, and it actually has worked unbelievably well. What I find amazing is because it didn't exist when I wrote my original proposal, it just came out of nowhere and gave me a validation plan. So you're measuring the carbon flux in and out of that tower at about 5-minute intervals is the direct measurement, and aggregate that in time, and you'll get a seasonal, a diurnal, and then a seasonal cycle of the CO2 flux of that site. And one of the things that's valuable to me is it isn't just one plant or one twig like I worked on as in graduate school. It's an aggregate measure of the whole system, maybe a square kilometer in radius. And that was exactly what I wanted. I didn't want a bunch of little detail of every planet. I wanted to know kind of in bulk what the ecosystem was doing, and that's what it delivers. And so we could then go to this is just an example of one of these tower sites, and we could go literally day by day and look at their measured gross primary production directly against our MODIS calculation of GPP. I could not have ever imagined a more direct one-on-one test of my algorithm. And there's something like 400 or 500 of these towers around the world nowadays. So that's been just tremendous for giving us confidence that our global NPP is overall pretty realistic most of the time in most places. There's always exceptions that wreck things. But it's developed enough confidence that we've had lots of good papers, got a number of science papers. This one was looking at the trend from 1982 to 1999 of global NPP using an earlier satellite, and at the time found a positive, an increase in global NPP over that 17-year period. And of course, the climate deniers loved it because they said this is proof that global warming is good. We knew that we would get this, and sure enough, out they came. Global warming is good. Another example of being able to look around the world was the La Nina in 2011. I got interested in that when I was at a talk where some ocean people said the sea level actually went down that year. And I thought, man, if the sea level went down and all that water got rained onto the land surface, I wonder what happened to NPP. And what do you know? It's the highest NPP we ever recorded, and we could identify the places that really just exploded in plant growth. And for once, it wasn't the Amazon. So much of our work, they just endlessly talk about the Amazon, and for once we found it, this enhanced NPP in the arid savannas. Now, we've done some other things with this. This was a paper about a year ago where we said, Jesus, they're drilling wells like mad all through the oil patch. I wonder how much of ecosystem service of plant production might be being lost. And so we got out our NPP data set and computed that, and found that we were losing about 4.5 teragrams of NPP over this period. And so another thing we've used with this NPP data set is to look at the role of forest mortality and disturbance, again, on the decline of net primary production on a global basis. So just some examples of, once we got this data set going, what are the kind of things we've been doing with it. Now let's go to the global carbon cycle. And of course, probably most of this crowd sees these data sets from the Global Carbon Project that comes out every year, where they attempt to assimilate all the relevant carbon data. I know there's a couple of people here in Boulder that contribute to this. And this is the track of CO2 emissions worldwide for every year. And we actually got quite excited because emissions went down last year. The only time that happened before was with economic collapse. And so there's actually talk that maybe we're starting to turn a big corner in carbon emissions. Well, when you look at emissions plus deforestation and say, where does the CO2 go? This is the global carbon balance in one slide. We know that about half of it stays in the atmosphere, and then the oceans in the atmosphere battle for the other half. And right now we're ahead. We think we get 30% and they get 26%. But the reality is this is in global carbon science what we are not satisfied that we can measure well enough. And so this is part of global carbon science in action, is trying to partition where the CO2 emissions go every year. Now, we've used our global NPP data set to look at that, and we combined the old satellite record from AVHR from back in the 80s, 90s, with our new MODIS satellite record starting here. And we put together this, this trend line. And for a while, I spent a lot of time trying to understand, you know, that like here's 2011, the big La Nina year. And of course, then we would look at some of the very lowest years and try to understand year-to-year variability. And finally, one day I was looking at it and I thought to myself, you know, in the global scheme of things, this overall interannual variability isn't actually very big. It's only about plus or minus 2% of the mean. And so this is suggesting that this key component of the global carbon cycle really doesn't have very much variability. And so that's when I started imagining, I wonder if this is kind of one of these planetary boundaries where the biosphere just really can't grow much more. So I thought, I went through and looked at a couple of, you might say, precursors to NPP, got out some of the global atmospheric data sets. And Mike, this is where some of you guys showed that, of course, we know that solar energy input is almost a constant, you know, plus or minus very, very tiny fraction. So from an ecosystem point of view, that's constant enough for us. What was more interesting is when I looked at global precipitation, and I found 2 or 3 different sources, and they again found that the final global total really didn't change much. So you have a huge drought here, and then you have a huge flood there, but by the time you add it all up, it seemed like within our measurement capacity, it really didn't change very much. And I thought, wow, do we really have some sort of global scale cap to some of these system dynamics? And I also, you showed me the global cloud cover also. And here again, it changes hugely from region to region. Then you add it all up, and suddenly the final global total doesn't seem to hardly change much at all. So I thought, maybe I'm onto something interesting here. Who knows? And so got this in Science in 2012 as one of those perspectives where every once in a while they let you just make stuff up and say whatever you want. You only get to do this when your hair is this color, though. There's something about age that helps a lot, I'm convinced. And so I went through this argument that it appeared like over 30 years of record, our NPP really was only changing plus or minus 1 or 2% per year. And I looked at the total net primary production and tried to partition, well, how much of it might we still have available? And this is known in our science as as human appropriation of NPP. And so there's been a good bit of work on this over the years of trying to say, are we pretty much using everything up, or do we have lots of spare capacity? And what I found was that And you can pretty immediately think, well, it's certainly part of how we understand climate stabilization potential. It certainly has some relevance to bioenergy policy, which I'm going to talk about again, in food security in a minute. And then it's part of our analysis of terrestrial carbon source sink. So I thought, okay, that's enough potential use that this is worth doing. And so this has been out since 2012. And so now I can cover some of the counter evidence, which is accumulating bit by bit. This was in Science a couple months ago. And what they're finding, this is from the combination of the CO2 flask record, the Keeling curve record, and the amplitude of the seasonal cycle they were analyzing. And what they're estimating, what they were seeing, is it looked like this GPP since 1980 has been maybe going up a bit, not a ton, but definitely not flat. One of the things that we have to pay attention to, and I think deserves some study, is net ecosystem exchange is different than net primary production. And so we're not quite talking apples and oranges here. We are talking about different components of the carbon cycle, and yet they're showing some positive increase. Now, we just had a paper in Nature Climate Change a couple months ago where we got out our satellite record and looked at the CMIP-5 land model simulations. And this is the array of the CMIP-5 model runs out to 2100. And what you found is they have some pretty huge increases simulated for NPP by the end of the century. And so we thought, well, how can we evaluate whether that seems right? So we got our period of record, which is only 1981 to the present, and we looked at the CMIP simulations against our satellite record, and our slope of increase is still positive. It looks like it's going up a bit, but it's only about a quarter of what the land surface models are suggesting. And so our conclusion was that we think that the current iteration of the LSMs is a little over enthusiastic on planned NPP. And I think a number of them know this also, but this was just out a couple of months ago. And then there was this yesterday. So this is in yesterday, and they looked again at the satellite record. They computed leaf area index, which is one of our inputs for our NPP calculation. They all use this old satellite record from AVHRR, which the NASA Goddard group has computed. It's known as GIMS 3G, for those of you that do this work. And then there's a couple of other teams that use that and MODIS together. Well, all three of them, they find a slope that is positive for increasing leaf area index over the last 30 years. And so I find this quite interesting. It does suggest that there is some flexibility to some perceived boundary. And of course, the most obvious is CO2 going up, because CO2 drives photosynthesis. And so in a way, we expect some kind of positive trend simply from the way increased CO2 enhances photosynthetic water use efficiency. And so we're actually seeing some evidence of some limited increase. So that's the state of affairs in the scientific realm. I want to take the rest of my time of taking this science and trying to attack some policy type questions. And so given the carbon, our NPP data set, what are some questions that we could ask with it? Well, this is the most fundamental one, is do we have enough global primary production for sustainable consumption by humanity. And if you pay attention to the demographics, this is where we think global population is going from about 7.3 right now, and we hope we asymptote before 9 billion, but I just read a couple of months ago a suggestion we may be at 11 billion by 2100, and so we don't know, but we know we're going to have at least a couple billion more people on Earth to support. And what I find interesting, this slide starts the year I was born, and it sinks in. The population of the planet has tripled in my lifetime. And that, when I think about that statement, I think, we can't do that anymore. So how are we going to feed all these? Now, a number of people in this audience work on various aspects of hydrology and water management. And this is a look from Agao Dai, from used to be NCAR, at water supply threats worldwide. And probably a number of you know of areas that regions that are very rapidly depleting their groundwater supply. So not only have we consumed our surface water supply, you think right now the Rio Grande doesn't reach the Gulf, the Colorado effectively doesn't reach the ocean. We've soaked up the entire surface water supply of some pretty damn big rivers. The Columbia still does pretty well, but we certainly in the U.S. show some evidence in parts of the country of completely using the surface water supply. This is how the GRACE satellite sees groundwater depletion, and all across the southern part of the country. And of course, groundwater depletion is, we call it mining. It isn't coming back in human lifetimes, and we're seeing clear depletion of groundwater. The fastest depletion I think they've found is in India, where they have 1.2 billion people to feed, and they have the fastest groundwater depletion on Earth, the last I talked to them. And so this is kind of ominous for global food production. We also know that we're already overloading the nitrogen cycle worldwide. That was one of the planetary boundaries. And so we have huge in-deposition and toxicity issues around the world. And then when you go to the food security crowd and start reading some of their projections forward, this is simply per capita food production from the present into the future, and these are different continents. The only thing to pay attention to is that this line is going down, not up, and not even staying steady. Is by their measure, they figure 14% per capita reduction by 2030 in global food production. Another study, same sort of thing for these four crops. The dotted lines are the demand, and the solid line is their model projected supply, and every single one of them, the supply doesn't meet demand by 2050 in their analysis. And so those are more targeted versions of this. Is this human appropriation of NPP that has a good literature established for 20 years, and this is a paper actually from a good while ago, but it's a good map, and it shows huge parts of the world where basically we are using the entire ecosystem right now. Huge parts of the world. And recognize this isn't only for food. This is food, fiber, fuel, food for animals production. This is how much is being used for the human activity in total, not just food production. But there's certainly a few areas where there's still a little bit of capacity left. But it does, when you start thinking decades into the future, it does give you some pause. A PhD student at in Sweden just did an analysis of this in a more regional sense. And so I wrote a perspective on his paper on a regional look at this human appropriation, where he dug down into local population, local meat production, residue recycling, specific crop products, and a lot of detail at a regional level to be able to do the same calculation. Are they breaking even in their use of NPP at a regional scale? And of course, this was for sub-Saharan Africa, and the answer was no, that they are falling behind. They are not in a sustainable path in terms of their consumption of their local plant production for this area. This is the kind of thing that somebody could do anywhere, and hopefully the answer wouldn't always be negative. But this was really a good example of going to a higher level of detail than just the big global scale. This is, to me, where things can get extra interesting. Okay, so we have biomass, and of course it's been our own Congress encouraged us to start making ethanol out of it. And so this has, over the last decade, become quite a topic in energy policy of should we be producing ethanol with our corn, or should we be eating it? Turns out people don't eat much of the corn at all. It's almost all fed to animals, and so we don't eat up hardly any of it. And so I kind of fell into the energy economics literature, and that was probably a mistake on my part, but you get bored with just looking at your own data set. And so we looked at a number of these projections forward of where's humanity going to get energy in the future. And of course, a number of these projections have these big wedges getting bigger and bigger for bioenergy. And that seemed in principle to be a good idea to people like us, I suppose. And so the number I want you to remember is 425 exajoules per year. And so this was by the end of this projection period, what this particular economic analysis was saying. Well, I was reading these in about, 2011 or so, and I thought to myself, I wonder if I translated this into units that I would recognize, what fraction of our global NPP is this? We know more about global NPP than anybody else. Let's go see if this is a meaningful fraction, or if it's really just, an incidental little piece that's no problem. And so we did. Had a paper in Bioscience about a year later, and basically this was a whole bunch of different estimates by economists of exajoules per year of total human energy use. And of course, right now we use about 500. And so you remember this one paper was estimating 425. A number of these, the highest one was 1,500. And this was actually in refereed journal literature. Okay, so we got out our NPP data, what we say is real NPP data, and here it is over here. And basically we start with about 550 exajoules of total plant production. And based on that analysis I talked to you before about how much is not available and not harvestable, and to cut to the bottom line, we figure if we can get 100 exajoules, that's the best we're ever going to do from bioenergy. So 1,500, not a snowball's chance in hell. Even 425, we do not see any way humanity can ever get 425 exajoules. And so simply by translating our NPP data set into energy units, we were able to point out that vast numbers of these energy economics papers were using completely impossible measures of future bioenergy. And that was kind of fun to do. In the midst of doing that, of course, I also got engaged with what should we be doing with bioenergy. And I'm becoming more and more convinced that we shouldn't be screwing around with ethanol to begin with. That we should be taking that biomass as directly as we can to electric power, and that liquid fuels have had it. I hope to never buy another piston engine ever again. I think they're doomed to the scrap heap of technology. So I make this projection right now. We'll see how long that takes. But the conversion efficiency of the biomass to electric power is about double the efficiency of taking it from biomass to ethanol and then power in a piston engine. Double. This was in Science in, where is it? In 2009, I think it was. Very interesting article. I recommend it. So here we are in the Anthropocene. This crowd knows all about. I don't know why I like this graph. Will Steffen with IGVP cooked this up years ago, and it just shows that by every darn measure you can think of, we've just had this exponential increase over the last century. And for my public audience, I find this one works better. This cartoon just summarizes all that other growth over the last couple of decades. You know, everything has gone up by 2, 3, 4 times. And meanwhile, the Earth hasn't grown one bit. And Edward Abbey summarizes it even more succinctly. And so I'd have to say that now I hardly read any climate science literature anymore, because any surprises I see are usually bad ones. And so now what pleasure reading I do is in steady state economics. And I love this quote of Robert Kennedy's: GDP measures everything except that which makes life worthwhile. And yet you see every country in the whole world, their economic policy is based on growing GDP. Every day of every week, we got to grow GDP. Barack says it at least once a week, and every other national leader. And yet there's this fringe of nut economists, and they really are a fringe, I'm sorry to say, that have been questioning this for a number of years now, that maybe the world can't handle a whole lot more growth of GDP. Bob Costanza had this comment in Nature just a couple of months, and it's about a year ago now, time to leave GDP behind. So this is the kind of stuff I read nowadays. If there's any social scientists in the audience, I hope you're proud of me, because I didn't read this before. But and so you find these, there's a few places that are looking hard at trying to challenge our standard economics dogma. And I actually think for at least a few of us in the earth science crowd, I think we have to start helping them. Because I think this is part of how we're going to get to the end of the century, is we've got to get off the endless growth of GDP bandwagon that all of our national governments are now obsessed with. And unless we do that, everything else we do is doomed to failure. And, you know, we've all seen this. And we all know that business as usual, what I call the Cheney curve, keeps us, I can say this in Boulder now. I wouldn't have said that in a whole lot of other towns, but I figure I'm pretty safe here, aren't I? But what's interesting for us to contemplate is this is a decision point, kind of back to that limits to growth. We are setting the trajectory for the rest of the century that might be very pivotal in whether we end up in Dick Cheney paradise up here or whether we end up with a stable climate. And for the young faculty and graduate students of the audience, I'm sure glad to hand this problem to you, because it's going to be a wild couple of decades. I hope I live long enough to at least get some sense of how we come out of it. So I was at the Fisk Planetarium last night, and one of the movies they talked about was The Martian, and this concept of how, well, if it gets too tough here, we could just offload to Mars. And how realistic is that? And of course, a crowd like this knows fundamentally how ludicrous that is. And so I like to end this way with reminding us how unique Earth is. So, and that's it. Thank you. Any economists here? That's who I really want to hear from. Of course not. They would never come to a talk like this. And that's part of the problem. How many of us have ever been to an economics lecture on our own campus? We got to admit, well, we don't go over there too often. That's their problem. Yeah. Yeah, that's right. No water stress is what I envy with them. One whole variable, they can just. Most their CO2 uptake is physical diffusion. It's not NPP. Their overall NPP is a lot lower. But there certainly is potential. I mean, aquaculture already, most of the salmon and shrimp, etc., we eat now are aquaculture. And so that is potentially part of some solution here that I don't try to touch. Yeah, I just don't try. Yeah, yeah. Mm-hmm. Yeah, we actually, do I need to turn something off or on? Oh, okay. Oh boy, good. Um, Basically, the quick version is, don't we have a lot of potential for improving agricultural efficiency? And the answer is absolutely yes. And there's some really good papers, you've read them as well as I have, that we can, um, in a lot of places, double agricultural output by very much enhanced efficiency. And so looking at this only from the food point of view, we have some potential solutions, at least for a few decades in food production, that are very realistic. The food waste issue, I've fallen into that as I look at this. 40% of the food grown never gets eaten. I've seen that over and over again. So we have ways to feed 11 billion people, well, certainly to feed 9 billion, maybe to feed 11 billion if we get smart enough. And so we may not have a lot of room for much else, though. And so, but I think this shouldn't be interpreted as suggesting that there's going to be mass starvation by 2050. If there is, it'll be for political reasons, not because the biosphere couldn't deliver the food. Yeah. Yeah, it would be if you started with some patch of desert and you planted and fertilized and irrigated, and up it came, our satellite would see that new growth and it would compute a higher NPP. Right, right. Yeah, we're not short on carbon, that's for sure. Yeah, we got all the carbon we need. Yeah. Well, it's certainly, oh, okay, back. How much do these trends in NPP rely on us understanding and predicting some of the climatological forcing, particularly rainfall? And definitely we see it every year. Where it rains more, you get more plant production, and where there's drought, you get less. So that's a real obvious response of the ecosystems that's quite direct. Uh, what's interesting for us to think about is whether we can imagine any kind of scenario where globally we would end up generating more rainfall because of more evaporation because of higher temperatures. Start thinking the whole Earth climate system and imagining, could we end up with a fundamentally different balance than we've had in the past? And especially with CO2 increase, I suppose it's possible. I suppose it's possible. Because the water limitation is the biggest limitation that we see globally. And more rainfall would then generate more plant production, as most of the places that on Earth. Yeah. Where and even time of year. Yeah. Yeah. Depends on whether you're trying to predict something or whether you just want to utilize it once it grows. And yeah, and of course, we always are being pushed for future predictions or projections. We sometimes try to wiggle out of responsibility. And and this is where I find it interesting to contemplate the entire climate system ending up in a different equilibrium than it's been in the past. And it seems that it's possible. It seems like from these different studies, like this one yesterday, that it does look like global leaf area is getting larger. It was a time integrated leaf area they were computing, so it's both leaf area times seasonal duration. And so there's some evidence that the biosphere is already responding with somewhat increased NPP. They didn't take their calculation all the way to NPP, the chickens. They stopped 5 yards short of the finish line. Oh, yeah. Yeah. Mm-hmm. Yeah. Yep. Yeah, and I think I went over that a little more quickly than I'd want to about the potential for future food production on a global scale. Um, just the raw biophysical capacities, uh, the single thing that we're most concerned about by far is running out of irrigation water. All these places around the world that are mining their irrigation water, Central Valley of California being the most recent exhibit. I was there a week ago. They're talking about areas that the surface has dropped 10 feet, 10 feet in the last 50 years as groundwater's been depleted in the subsidence of the land surface. And those sort of things reduce our food capacity in some pretty key areas pretty significantly. And so there's also been lots of studies that show for certain crops in certain regions that warmer temperatures is not going to enhance the growing season. It's going to overstress the plants. And there's been a number of papers on that in the last few years. Now, whether the plant breeders can keep ahead of that genetically for some period of time is yet another variable to throw into the mix. But running out of water is pretty fundamental, and I think of India. Oh my God. You think of how many hundreds of millions of people that live pretty close to hand to mouth, and they're already predicting in some of those agricultural areas when they'll bottom out their groundwater. They know it's coming. Yeah, in the wellhead, 10 feet a year. Yeah, yeah, and so you imagine that can't go on for very many more years, and the number of people relying on it is just, it's like 100 Montanas all at once. Anything else? Okay. Yeah. Yep. Yep. When there's only about a 500,000,000 people on Earth. Yeah. Yeah. All right. Yeah. The question is, can any of these biophysical limits that I'm suggesting here ever end up in economic models of GDP or GDP limitations? And the economists work with just totally different variables. They just, I've in my reading, I'm just astonished at some of their models. A favorite slide. I didn't use it today, but I did for a number of years. It was when Alan Greenspan was testifying in front of Congress after the 2008 collapse, and he quoted, I'll probably get it slightly wrong, but he said something to the effect of, well, turns out there was a variable in the economic system that we don't have in our model, and oh well, we lost $5 trillion in a month. And I thought to myself, well, you sorry sons of bitches. Our GCMs are way better than your GEMs, and yet you guys get all the respect and we're nothing. We sit up here begging for peanuts. And I really, it got you thinking that for all the notoriety of economics, I think our Earth system modeling is orders of magnitude more complicated than theirs, and yet they think they're so cool. So I'm on a warpath with the only good economist is a dead economist or something. Give me a beer and I'll say anything.